Welcome to this DevSecCon Germany meetup, right? So this is our second event of this format. So our idea is it's vendor neutral, right? It's of course it's organized by Snyk, but then it's vendor neutral. It's not a marketing salesy event. It's more really community oriented. It's part of the DevSecCon global community, right? It's an inclusive community that educates and enables developers in application security. That's the purpose of this kind of meetup series. So this is our second event. It's a monthly event. We try to run the series every month. We do have a website. It's called devseccon.com, where there's also a link to a Slack channel. So you're also invited to join the Slack community, ask questions there. Just about myself, I'm Matthias. I'm a solutions engineer at Snyk. I'm basically hosting the event, but most importantly are our great speakers. So
thank you so much for joining this talk, everyone. My name is Agata, and we're going to speak with Daniel today about how we discovered vulnerabilities in Go binaries in the container space. So we're in a container group, which basically means that our space is finding out vulns in your images. They can be in your container registry, or you can be using our CLI product maybe in your CI, or also we can monitor your container runtime in Kubernetes, so your live application as well. So this is basically the space that we're going to cover. So let me take you through the agenda for today, for this talk. We're going to talk about the problem space of actually detecting the vulns in compiled languages. We're going to take you through detecting binaries in container images, inspecting the binaries, so how we actually parse them to get the dependencies and then vulnerabilities, how we extract that dependency data, about our limitations we're going through as well, and then we'll briefly take you to what's next for us. So let me introduce you to the squad. My name is Agata, and I'm a software engineer in Snyk. I've been in Snyk for over a year now, which feels like 25. And I also have a small puppy who might interrupt us. So apologies for that, but luckily she's sleeping now. And I had a big pleasure to work on this feature with Daniel. And Daniel, would you like to introduce yourself?
Yeah, sure. Hey everyone, my name is Daniel. I've been with Snyk for around 2 years, I think, and currently I'm an engineering manager in Container Group. I'm a former software engineer, so now I'm allowed to think that array starts at 1.
Thanks, Daniel. So probably the word binary comes out quite a few times in this talk. So maybe someone can count it and tell us later how many times it is. So now Daniel is going to take us through this the problem space of detecting vulns in compiled languages.
Thank you, Agata. So as you might know or don't know, Snyk is a platform that gives you ability to scan your source code for vulnerabilities in open source libraries. At the beginning, we started for scanning your manifest files like package.json and package.log.json for NPM, pip file for pip, POM.xml for Maven. Then Snyk introduced its container offering, so we get multiple requests from customers to get visibility not only into OS package vulnerabilities, but actually in the application running inside. So initial challenge that we encountered was there was a difference between scanning compiled and interpreted languages application inside. But before, let's look a bit what is compiled and interpreted languages. Next slide, yes. So as you might know, this is 2 big groups of the programming languages we are using, and I'm just gonna name few. Like compiled, as you can see, it's like Rust, Java, Go, C group. Also interpreted are Python, Ruby, JavaScript, and Lua. So to explain it a bit easier, next slide, please, Agatha. Yes, and what can be easier to explain compiled and interpreted languages than explaining a hummus recipe written in Hebrew? Next slide, please. So think about it. Imagine you want to cook a hummus, but only thing you have is recipe written in Hebrew. So for you, as an English speaker, there's a couple of possibilities. So first one of it is you actually have this recipe translated for you into English. So you and anyone else who speaks English could read the English version of the recipe and make it. So think about this translated recipe as a compiled version of recipe. The entire translation is written beforehand for you. If author decides to swap the olive oil for another olive oil, the entire recipe needs to be retranslated. On the other hand, you have a second option, which is interpreted version. You have a friend who speaks Hebrew. He sits right next to you, and the moment when you decide to make a hummus, he'll go line by line and translate you into English the recipe. So your friend is now an interpreter, and the recipe is interpreted version. So interpreters run through a program line by line, and execute each command. If the author decides to swap something, it's going to be translated on the fly. Next slide, please. So yeah, let's take a look into our container for interpreted language, for example, Node. So you know that inside you can have a package JSON, and when you install in your container's dependencies, you just run npm install, you still have a package manager inside your container to run it usually. So if you can have a next slide, please. You can see that we have here clearly stated package JSON and package lock inside. And understanding what third-party libraries you're running inside your application is easy as basically inspecting these two files. On the contrary, next slide, please. Go applications are compiled language, and there is no package manager deployed together. So whenever you go into container, there is no package manager to query it for packages there is inside. So on the next slide, you'll see that you just have standalone binary that you can do nothing, only execute. Next, please. And giving back to you, Agata.
Thank you, awesome. So now, next slide, we're going to talk about detecting binaries in the container images. So our first challenge is to find your application. So we have a container image, let's find the application. In order to do this, Snyk basically searches through the image file system, inspecting each binary to work out as a Go binary. And let's take a step back in here and have a look at the slide now. I would like to briefly talk about how we actually scan the image. So we're touching here on the core of the container scanning in Snyk, which actually it's my team's responsibility now. So you have a container image. Maybe it's in your private container registry, maybe it's in Docker Hub, maybe you're running our CLI, our Snyk CLI in your CI pipeline. So it doesn't matter which product you use, we use a core library for all the scans. What we do is essentially save the contents of that image file in your file system as a tarball, and we parse it file by file. So now we inspect, we found some binaries. We went through all the files in the container image, and let's say we found a bunch of binaries. Now we want to know if any of them is a Go binary, if we're dealing with a Go application. So to do that, in the binary file headers, we look for either Go build info or note Go build ID sections. If one of them exists, we know the binary is a Go binary. So Go build info, as we will explain a little bit more in detail in the next section, will point us to the address in the memory where the Go module's data is stored. So this is what we're really interested in. So as you can see on the right-hand side of the slide, I've got a human kind of readable ELF output in here. So ELF, it's a binary format that we've tackled first. We will speak about this a little bit more in detail. So if you want to have a little bit of play to see that, I've used ELF utils, which is a part of bin utils tool. And on most Linux distros, it's actually available. But if you're on macOS like I am, you can install it with brew and kind of have a look through your headers and a lot more in your ELF file. So, okay, we found a binary, a Go binary. Let's inspect it now. So now we need to work out which Go modules were used in the original source code. Luckily, Go versions 1.11, this is already have the functionality to do so by storing the module information within the headers of the binary itself. So we can see this in action by using go version m command. And in the console output in here, this is exactly the output of that command. So the challenge for us, for Snyk, for our squad, me and Daniel, was that Snyk CLI is actually written in Node.js. So we needed to replicate the functionality of the Go version M. So what we see in here, so it's actually available in the Go source code in our Node code. But now let's first of all take a look at the ELF binary format. Oops, not that ELF, another ELF. ELF executable. Oh, my puppy, hello. So ELF is a abbreviation for executable and linkable format, and defines the structure for binaries, libraries, and core files as well. ELF files are typically the output of a compiler or linker and are a binary format. So we chose ELF as the first type to be analyzed, as it's a commonly used type for Unix and Unix-like systems. And here we have a fun fact. It's used in the Linux kernel, for example, in Android and PSP, PlayStation, Wii, and also in Samsung OSs. So by design, ELF is flexible, it's extensible, it's a really cool format, it's a cross-platform. So for instance, it supports different NDNSs, which I will talk about as well, and address sizes. So it does not exclude any particular CPU or hardware architectures, which was quite important for us as well. And another fun fact, an ELF binary will always start with a specific magic number. So it's a mandatory header that all the binaries have, and we've used it to determine the file type as well. So I thought this image represents NDNS the best of all the images that I found on the internet. So it is NDNS is essentially the order of a sequence of bytes in the memory, of a sequence of data in memory. So it helps to interpret the remaining objects correctly within the file, which was super important for us when we were writing this code. And this is important as different types of processors deal differently with the incoming instructions and data structures. So a little bit more detail now. So big endian systems store the most significant byte of a word at the smallest memory address and the least significant byte at the largest. Now, the little endian, least significant byte at the smallest memory address and the most significant at the largest. So if none of what I said makes sense, have a look at the piggy and hopefully it should be a little clearer. So basically the least significant, the little endian is the reversed order of the big endian. And let's have a look at the example on the slide on the left hand side. So let's suppose we have an integer stored in 4 bytes, 32 bits, and then a variable y with the hexadecimal representation of 0x01234567. So it's stored in 4 bytes. From the left-hand side, it's 01, 23, 45, 67. So that's the big endian. And while on the little endian, on the right-hand side of the slide, it will be stored in the reverse order. So 67, 45, 23, and 01. So now going back to that ELF file and its structure. So each ELF file is made up of one ELF header followed by the ELF data. The data can include, can and don't have to, program header table describing 0 or more memory segments. It's used in runtime. And then the section header table describing 0 or more sections. So sections and segments are two complementary views of an ELF file. So segments, it's used for the linker to allow execution, and sections for categorizing instructions and data. And now stay tuned as this is exactly where we're going to find the information that we need a little bit later. So now I wanted to show you an example. I've got a Y-cube binary in here. So I'm using, it's the same tools, the binaries that I've used before. So YQ is a lightweight and portable command line YAML processor, and I'm just using it as an example here, so we can have a look at a few of that through that ELF architecture. So we can see in here at the top, we've got the magic number. We can also see that our ELF is using a 64-bit architecture. In the third line, we see it's a little endian. In this case, in our case, this particular file. And there is also some other interesting data like the number of section headers or the number of program headers, which might be relevant. And back to Daniel with how we actually extracted that dependency data.
So as now we know everything about compiled languages, interpreted languages, ELF, NDNSs, let's actually go in and understand how we did it. So Agata mentioned before that the Go version -m give us all information about Go modules, packages, and versions that were listed in your Go sum file. So this is actually the information we are looking for. So what was the easiest way to understand how Go version -m works? Look how Go tool itself works. So we literally went through the Go source code and replicated in our Node.js plugin to do the same. Yeah, thank you. So first of all, we're interested in where this data sits in the file, and we can find this out in 2 ways. To retrieve data about Go modules, we found we would need to explore meta sections of ELF Go binary. We initially are focused on the Go build info ELF section, if it exists. This ELF section contains valuable information for the scanning process. ELF segment that contains Go build info, pointer size, it's either 4 or 8, depends on 32-bit or 62-bit processors respectively, big or small endian, as well as pointers to Go version that was used to compile, and Go modules information that we actually looking for. If the Go build info ELF section is missing, we are going to retrieve from the load segment's virtual address. Next, yes. So in this slide, you actually can see that there is a build info blob left by the linker, and it's identified by a 16-byte header, consists of 2 parts. First, you can see on the first picture is a build info magic that will be in the segment pointed that we found before in the Go build info. And also you'll have a pointer size. So as we mentioned, it's 4 or 8. And as well, is this binary is a big endian. So now we have all this information, we can actually dive in. Yep. Next slide, please. So here's a simple how we did it. It's literally how it Go does this. Next 2 multiplied by pointer size bytes will contain 2 pointers. First is to Go version of the package, and second one is to module itself. So now we can retrieve the data for modules and versions. Next. Yes, so now we have Go module and its version. But one thing that we're missing is a package name, because Snyk needs 3 of these pieces, as I mentioned before, to get your vulnerability information. So let's have a look in a string tab elf section. So this section can only be found in non-stripped binaries, and I'm going to talk about this a bit later in the limitations. It represents all packages stack data. There you also can find how Go initialized its packages by looking at calls to .init task. This is a Go internal marker for initializing new package. So you can see that info will look like this. This is URL like module name that we already have. Then you have a package name and the init task itself that we will omit in the end. So basically what we need to do, we need to retrieve this, match it with the module names we have, and from it get a package name. So this is what it actually does. It's super simple. It's basically parsing the section, doing some small manipulation and getting this. So now we have all information needed to understand vulnerabilities that come from your open source Go modules. Go module, package, and version. Using these pieces, we'll build a flat dependency graph because we cannot restore relation between modules. Unlike in Node.js, when we have package JSON and package log, we actually can understand which package is a transitive dependency of another package. So here it's going to be only a flat list. And limitations that we encountered is this is a first release of the feature. Yes, thank you very much. So for now, we're doing scanning only for ELF executables. We're considering extending it to also support Macro, PE, XConf, and other binary formats. As I mentioned before, non-stripped binaries only. What does this mean? It means that string tab ELF section is stripped, which contains all the relevant package info that we were looking for. So when compiling the Go code into binary, if you add SMW linker flags, Go will strip all this debugging data out of the binary. Next slide, please. And also binaries that were built with Seagull flag. What does this mean? This is a marker for the Go code that doesn't use Seagull tool for interacting with C code inside Go's code. And last one is no vendor dependencies. Vendor dependencies is actually when is no kind of old concept in a Go, when you pull source code of your dependencies and build them in the compile time. I think that's it for the limitations. And Agata, getting back to you.
Thank you so much. So I'll very briefly talk about what's next for us and this feature. So upcoming iterations would be focused on solving the limitations that Daniel just talked about and which were introduced by this first iteration. We're going to have a much deeper dive in how Go creates its ELF binaries and where it stores all the data to overcome those limitations basically in the current feature. And that's basically it. Thank you so much, everyone, for joining. And thank you so much, Daniel, for spending all this time coding with me. That was super fun. And yeah, hopefully, I think now it's time for questions. So if anyone would have some questions, we can answer them.